recording. We're now recording. Okay, so let's take a look at this is ITS 365 foundations. And we're just going to create a new script. All right, so today's topic is the perceptron. So we covered on Monday's lecture, we basically went over a little bit of the history of neural networks, right? We went over the context of neural networks. And that's an important thing, I think, to know the history, just because it really emphasizes why, right? So like we teach a course called 470 parallel computing. Why is that relevant? Well, it's relevant because without that, we can't do AI, right? So having computing power is really important. Jobs in a CPU can take 5 days, on a GPU will take 12 hours. And that's a significant difference, actually. Okay, so those are important, the hardware. And that's why, you guys who work in, IT as a major, cloud and networking and computers, are part of it, right? So it's like you already have a lot of the background on the infrastructure, which is really important. And then there's also the component of understanding how the foundations of the algorithms. And then, of course, there's the application and applying to multiple problems, okay? So we are going to, as we went over the lecture on Tuesday, I just motivated the history of neural networks. And I said that at the end of the story, well, not the end of the story, I should say, where we are in the story right now is with deep learning, right? That kind of became popular since 2012. So really like 10 years, deep learning as a field has only been around for about, that is, something that we can implement, for the last 10 years or so. And so all of this dates back, as I said in the lecture previously, it all dates back to the 1940s, when you actually started to have computers where you can implement all the math that existed from, previous centuries. So in 1940s, we talked about Rosenblatt and basically the creation of the first implementation of these ideas on a computer, right? We're talking about, vacuum tubes here. So if we look at Rosenblatt and the perceptron, you can probably find a picture of him. Yeah, here it is, actually. You see, this is what we're talking about. Frank Rosenblatt, 1950, works on the perceptron. So this is it, right? So today's algorithm, dates back to, was meant to run on that machine. And that was pretty exciting back in 19. All right. So you can, there's a very nice, interesting story about all of this. You can see there, that was the idea of what they were trying to do. They were trying to find images, shapes and images. I think it was very simple shapes, like squares and circles and things like that. So you can see kind of an important person there. Okay, so let's go ahead and focus back on the perceptron. So now we're going to implement the algorithm in today's class. So this code is already, as you might expect, is already on the GitHub. So you can just get it from there. But I'm going to write it up just to get an idea. It's under the machine learning foundations and then within neural networks. So I put everything related to neural nets in a specific directory. So actually, I'll point that out. We go to, I don't know if you guys, yeah, I didn't share the screen All right, so go to the GitHub here, under machine learning foundations, neural nets. Pretty much everything that we're going to be doing in this latter half of the, or the last part of the semester is here. So we'll be doing the perceptron today, and then next week, linear regression, logistic regression, multi-layer, and finally, TensorFlow. Okay, which is still Python, but instead of doing import numpy as NP, when we use TensorFlow, we're going to use the same thing, import numpy as NP and import TensorFlow as TF. That's the additional component, right? Because now we're going to need a more powerful thing to work. Now, it is my theory that NumPy will eventually be its own TensorFlow. You know, if you think about it, NumPy was the original one and everybody really copied how they did things. So NumPy was really made to make linear algebra more efficient. And TensorFlow and PyTorch use linear algebra extensively. And so, you know, TensorFlow and PyTorch were made in the image of NumPy. And so it just makes sense that NumPy eventually will say, well, maybe we should also add the GPU support and everything. Okay, but anyway, so we start at the beginning. So this is the code, the perceptron. So we're going to go ahead and, you know, so I pointed out where it is. So let me make sure I'm in the right. So everyone should be seeing the Jupyter notebook now. Okay. All right, so the perceptron then, we're going to start there, how it works. It's actually nice because what's really great about all these algorithms is that they're really incremental, right? So if you understand the perceptron, you understand already, like I would say, close to 50% of deep learning, you know, and it just starts adding on. And just before we make the jump to deep learning, we already get 80 to 85% of it. It's just a little tweak that we have to make that makes it deep learning. But that little tweak required decades of progress in hardware and in other areas, right? Some algorithms that we don't see in the background, like I said, like back propagation, gradient descent, and all of those. I'll talk about some of those algorithms, you know, as we go through and into more advanced topics. Today, really, though, we will talk about, in essence, how an algorithm learns, okay? And so that will be the main idea. So let's get started then. So we're going to import some, we're going to use some libraries, the same ones we've used in the past. So import numpy, as you've seen this semester, I've tried to keep things pretty consistent to numpy itself, and pretty much everything has been in numpy. We are also going to use sklearn just to be able to use some of the data sets and some of the features of sklearn. So from sklearn, model selection, from sklearn model selection, import train test split. Okay. And we're also going to, from sklearn, we're going to import data sets. Right? And data sets will allow us to, you know, maybe create some random data or just use some data in general. Okay, so that's the idea. So again, let's just start with the high level of what we're going to do, right, before we get into the specifics. But usually, you know that in general, whenever we're talking about a model, right, you know, we have a model, we train it, we test it, right? Those are basically the ideas, and we need some code for the data set. So let's think a little bit, you know, this is supervised learning, right? So this is one important thing to remember is this is still supervised learning. It's very much knowing the X and the Y, right? So that's really the idea. So here we're going to have X, comma, Y. And so now, you know, we're going to create our data here. So we're going to use a feature in sklearn. So in the datasets module of sklearn, we have a feature called make blobs. Make blobs, okay? And so this allows us to just create data, you know, randomly, basically, so that we can, you know, have something. Okay. So we're going to create, a data set with, let's say, 150 samples. And samples equal 150, comma. And then we're going to do n features. And this will be, 2 features. So it's the x is 100 and the matrix, the x matrix is 150 by 2. Okay, so that's really important there. And then because we're creating data sets, right, 2 classes, then these classes, we always assume the data comes from distributions, right? Data distributions, So there's a cluster here, so that cluster can have a mean and a standard deviation, right? That's pretty standard. And so here we can basically say we want 2 centers, and that's to imply that the data should come from here. So we're going to first create the 2 centers and then get our samples from there, okay? So we're going to say 2 centers, and we're going to say that the clusters should have a standard deviation of about 1.05. And that just allows us to define a spread for, how big or small the cluster is going to be. Does that make sense? So we're creating 2 groups of data. It's like I throw some of you there and some of you there kind of randomly, and then I figure out where your means are and your standard deviations. So then after that, I take the samples from it, right? And then we always can use a variable called random state. I can use random state, okay? And random state, just give it some value. This allows us to control the randomization. So if we always want to get the same randomization, we use the same random state, which is the seed basically value. It allows us to control that. All right, so that's it. So instead of using iris here, I just created a random data set, right? Now I'm going to use this data set to do, because it's supervised learning, to do the training and the testing. So I'm going to create 4 matrices, X train, X test, Y train, and Y test. So this is pretty consistent to what we had done in the past. So X train, X test, Y train, Y test. All right, and we're going to use the train test split. So we're going to use train test split to split our data. So we take in X, comma, Y, right? And we're going to say that we want the test size to be, let's say, 0.2. So 80% of our data we'll use for training, 20% of our data we will use for testing, okay? All right, and then the random state, state is going to be, again, 123 or whatever, some value that just allows us to always get the same randomization, the same split basically. So now we have our data sets here. They're ready to go. And so now we need to, so this is the same as iris, right? I just did another data set. Imagine if this confuses you, just think, oh, this is iris, 150 samples. Instead of 4 features, it's got 2. And instead of 3 classes, we've got 2 classes. I just created some data randomly. So we could have used iris or MNIST or whatever. All right, so we have our data set here. Now, the thing that we need to do is we will need to create a model. So we have this idea of creating a model, basically. So usually we could create an object called model, and we could create a class, and then it's going to have a couple of functions, train and predict, okay? But what happens here is that we are going to need a couple of functions, right? So we're going to need basically 2 functions. We can give them any name that we want. I'm just going to call them fit, which is train, right? And then predict, which will be once we've trained the model, now we're going to predict on new values. So that's basically all that's happening here. All right, so here, let me grab the tablet actually. So we're going to learn basically an intuition about neural networks and why they're called neural networks. I'm just going to create a graph, right? We're going to switch over to the whiteboard here, because this is actually really important. So what we're doing is basically, I have some data, right? In my case, let's just look at the case of Iris. I have some data, X1, X2, X3, X4. So we usually, because it's a neural network, we just represent things as neurons, right? So this feeds in there. All right, and then our objective will be to predict a class, right? So the class can be, there are several ways of representing. We can do one neuron, which outputs a value between 0.0 and 1.0. So basically here we can say, if this value, right? So if value is greater than 0.5, then basically we say it's class 1, else class 0, right? You see that? So that's basically one way of doing it. Another way of doing it is, which is actually, this is the way we're going to do it today. But another way of doing it would be what is called one-hot encoding. Neural nets also support this, and this will be more of a later that we will cover this. But if we have two classes, then we have two neurons, right? And basically what you would want is this should output a vector that says 0, 1. That indicates this is the class. Or it outputs a vector 1, 0, in which case this is the class. You see, so that's another way of representing classes. If I had 3 classes, then I can just say, you see, and I have 3 neurons. And so now the representation would be, and that's the class. Or the representation is, and that's the class. Or, right, but it's always like this. And this is called one-hot encoding. So this is something else that's coming, right? But for now, we're going to limit basically what we're doing to just something similar like one neuron, right? So outputs a value between 0 and 1. As long as if it's a 0.5, then it's one class. Less than 0.5, another class. Now, the thing is, what is happening? The question is, how do you, let's use the example of 2 neurons, right? So 2 classes, cat and dog, for whatever reason. All right, and so let's think about this example, right? So you have your inputs, and the inputs are things about the picture or things about the, whatever the features are, right? But you need to basically connect this with the input. So one simple way is just to add a link here, right? And then you're going to have weights, W1, W2, W3, W4. You see that? And those are the weights that connect that. Or, but that's just for one neuron. Then I have the other neuron. It's difficult to draw on this. Okay. You see, those initial inputs are connected then to the other one. And this has its own set of weights. Notice these are red. You see that? So for this problem, how many weights do I have to learn for this specific one? 8. I have to learn 8 weights. You see that? Plus 2 biases. So actually B1, B2. Right? That's because it's the line equation, right? Plus B. You just remember that. So we also learned that parameter. But to keep things simple, let's disregard that one for now. And these are called the parameters of the model. This is just a linear model. It's got no nonlinearities, and it's not, it doesn't have any layers in between, you see? So really, we basically can only learn this, that if we look at these 4 inputs, is it this one or that one, based on the weights? And that's it. That's all we can learn. But neural nets then say, well, what if in between I add another layer of neurons? You see that? I just added. This is called architecture. So now I'm adding a new layer of neurons. And now what happens? Notice what happens here. Now, before you get to these, you have to go through this one. So you create the links. They're already pre-created. You know, hence the name neural networks, right? So, and then now I do this. And now I do that. They're all connected. But I don't know what the weights are, right? So we need to figure out what these weights are going to be. W, so I'm just going to say WI, you know, W, and there's more now. More weights. You guys see that? There's way more. So there's 4 times 3. So now there's 12 weights that we need to learn. But what about from here to there? Well, we also need weights for that. Because we have the connections in the architecture. But the training process involves learning again these weights, and these are different weights. Let's use J. You see, and now you had the 12 plus you have 3 times 2 is 6 weights. So it's 18 weights. Do you see that? And we have to learn every single one of these. That's it. That's machine learning. That's neural nets and deep learning and everything else. That's this. So you start now, because we have a train set. What do we know? We've got some values here. We've got some values 0.2, 0.1, 0.7, 0.003, right? Those are the values. And we know that whenever we get this feature vector in the X data, we also have the associated Y, which basically, let's say it's 1, 0. So we need this, right, as an input into the model. Initially, when it's not trained, what is the value of the weights? 0, or it can be random values, okay? So then we run the inputs through this model, and what is the model going to do? It should give us one of these classes. Do you see that? It should give us. So let's say it predicts actually 0, 1. So it did it wrong, right? But this is where you now take the predicted versus the real, and you're going to compare the values, right? So you're going to compare to see if you have a match or you don't match. And based on that, so that's the feed forward. Remember that I talked about the feed forward algorithm? So you go from here to here. Once you get here, you have to compare predicted versus actual. So you'll see that. It's usually just taking the difference of the outputs, okay? And then once you have this information, you need to find a way, and this was the problem for the longest time, right? You need to find a way to take these results and what is called back propagate them. So what that means is what? With this information, now you're going to go into these weights and say, well, WJ plus something, which could be negative. And that value is going to adjust the value of the weights. You see that? And then we back propagate to this. And then with these values, we back propagate to that. And we just go all the way back. Okay? So the 3 algorithms that come into this are called, as I said, feed forward, back propagation, and gradient descent. Those are the 3 algorithms that solve this problem. But intuitively, this is what we're doing. Now we can also actually, now this with 1 input layer, 1 hidden layer, and 1 output layer. This is the famous multi-layer perceptron. This is the one that you guys did in WECA, right? What we're doing today is just a perceptron. It's not even this. We don't have hidden layers in today's algorithm. You guys see that? But it's still the very basic without these. So if I take all this out, so our perceptron is really just this. A multi-layer perceptron is that, because it's got another layer. And a deep learning algorithm, believe it or not, is just one that has one more than this one. So it can be as many as you want or as few as you want. So what I mean is this is the input layer. You always have that. This is the output layer. If we only have one hidden layer 1, then this is going to be called a multi-layer perceptron. But the second we add one more, hidden 2, all the way to hidden n, guess what? It becomes deep learning. That's why it's deep learning. It's a deep network. You see that? So now if I add 2, 3, 4, 5, it just becomes deeper and deeper. Right? So there's something called ResNet is a famous algorithm for convolutional neural networks. Can't remember how many layers it has, but it has many layers, right? And it's a standard thing that a lot of people use. Transformers have tons of layers. Okay. So what is the intuition about this? Well, the intuition is this. So if you just had 2 layers, you see, let's say that, take the classic example of an image of a cat. Right. We have a cat there. Okay. All right, so we have a cat there. Kind of crooked. All right, so we have a cat here. If we only have, let's add more layers and just think of the intuition of why, in theory, a deep neural network can help us to find cats and dogs, right? If I just have the input like this and connecting directly to, is it a cat or a dog? That is the equivalent of just, at this point, all the machine can see is basically like a whole bunch of points. That's it. It's not really seeing any. You see that? That's all it can see. However, as we start adding layers, something starts to happen. Because we have the input and we have the class, right? So remember, we're training. So that means, we're training, we've got this input here, and we know it's a dog, actually. So then if we have a picture of a dog, just to kind of do the difference, dogs, for whatever reason, have the drooping ears, right? So just to make it simple. So that's a dog. Okay? So whereas the cat has the pointy ears, like that, just to keep it simple. All right, so initially, when we looked at both images, the algorithm just sees that. So yeah, of course, it's going to have a hard time knowing which one is a cat and which one is a dog. Do you see that? But it's got training data. As we add more layers, we add more neurons. So these neurons, you can think of them as filters that help to identify things. So now let's say that these 2 neurons here are the ones that focus on the ears. All right, they focus on the ears. So these start to fire together whenever it sees. Now let's go over here in the second layer. If we're almost like visualizing what the second layer is looking, right? Now the second layer is starting to construct things like that. Whereas here, the second layer is starting to construct things like that. Do you see that? It doesn't quite yet see ears, but it starts to see the building blocks of them, because it starts to see the pattern that it's seeing these more straight lines, from the original data. If it now joins the original raw data, it starts to see straight lines, whereas here it starts to see these curves. So whenever it's dog, it's seeing this. Whenever the word is cat here, it's seeing that. Do you guys understand? But it's not quite yet complete, right? And so if we add yet another hidden layer, what might happen is this one notices that there's like the pointiness, right? The pointiness. Whereas for this neuron, it might notice that there's, that shape, actually. You see that? It's kind of taking it's seeing a pattern of things where you just see that, oh, I see all green there, right? And then when I group that all green, but then I see some straight lines and green. And then I see some black blobs also. And I start putting things together to identify, oh, that's a set of tables with computers. You know what I mean? So it starts to build it like that. So in the second layer now, it might take that input and that input. You see? The pointiness plus the straight lines, plus this one actually. And so now it starts to see that. You see that? It's starting to see that. Whereas for this, for the dog, and the dog may actually be another set of neurons, right? So the dog may be this one that fires, but now the dog is starting to, or sorry, the model for the dog images is starting to see that. You see that? Yeah, go ahead.
So it's sort of understanding more complex features based on all these.
Such a perfect way to put it. Yes. Very nice. Very eloquently put. But it's exactly right. It's exactly right. It's like it's figuring out things, and it's filtering out things, exactly as you said it. So it looks at the raw data first, but without enough layers, it can't make the connections that are needed, right? And so it's exactly like what you said. And so now we have, but here still, with this may not be enough, right? And so that's the intuition where if you add another layer, guess what? This layer now finds a connection here, right? And by the way, this one was noticing, you know, it was going through here, and it was going through those two, and then now this one here was noticing something about the cat as well, that the cat had that as well, right? That as well. Whereas the dog had this as well, this as well, this as well. You see that? And now, but still, we have no connection, right? And then maybe in another layer, each layer is building on what the previous one kind of noticed. You know what I mean? Like it noticed a little bit, little details. First, it just notices like points, and then the points start to become little like curves or straight lines, and then you start joining together the little straight lines and curves until you start creating shapes. Yeah, because the important thing is you have inputs and you have the label, right? So remember, it's not noticing everything. It's only noticing the difference between cat and dog. That's really important, right? And that's why I've done this example. Notice I haven't said anything. You know, they both have a smiley face, right? You see that? Smiley face, smiley face. They're kind of similar. So what's the machine learning algorithm doing? It's actually ignoring the smiley face because it doesn't see any value in what it's trying to do, which is differentiate between the two images. So it focuses in on the things that are different versus the things that are similar. That's in essence the goal of machine learning. Yeah, go ahead. Yeah, exactly. Exactly. So that's a very nice way of putting it, actually. This is a neuron for the smile. You said it, right? The things that are constructing the smile, let's highlight that as green. Actually, that's a color I haven't used. So the smiles, these are the first initial points of the smile, then the curves of the smile, then these two together, the smile going up, so it's a smiley face. So if it was trying to determine if happy and sad, this would get higher weights, because that would be the problem, because the classes wouldn't be cats and dogs, but would only be happy and sad. You see that? But here, we don't care about happy and sad. They're both happy. And so actually the goal is to focus on whether it's cat and dog. And so as you said, here, the weights could be like 0.6, 0.7, high values. And as you said, here, these are practically, they're there, but they're really tiny weights. So basically, it almost becomes, in a sense, then, the equivalent of they don't even exist. Those weights, the neurons are there, Oops, I didn't mean to do that. Yeah, so it almost becomes like the neurons are there, but there's no connections between them. So whenever it sees this input, it will never fire all the way to here, in a sense. Well, think of it in terms of like electricity, right? You saw that things about the phase, but the electricity never makes it to the class because it's irrelevant to the problem. It learns only the path that has to do with differentiating a cat between a dog. And here I picked conveniently the ears because they're very different. You guys see that? And then in this last layer here, you know, it might connect that one and that one for the cat. And so now what the machine at this point in the network, right? So at this point in the network here, at this point in the network, it might actually be seeing that. You see that? And only that. It's almost like the original image now only looks like this, literally, in a sense, right? Intuitively. And so for the dog, it's kind of the same idea. It's got its own neurons over here, right? That came from somewhere, I think it was from here, right? And then these neurons are actually now just seeing in the image of the dog. Like that. And it helps a lot that the images should be the same size, so 28 by 28. So that this is really important actually. And that the ears are kind of in the same place. So that helps a lot as well. So because again, it's only trying to tell the difference. So if you notice, that's why whenever you know, let's say sometime you were told to use machine learning, right? You know, you probably know that if you've ever traveled, right, overseas, when you come in, right, your passport gets checked up and everything. Well, your passport, you're standing like this, there's a white background, pretty much everyone's at the center, right? And the idea being that for the algorithm, it's going to be a lot easier if things like the ears should be like almost exactly in the same spot. So that way, when it focuses on the pixels, right, it's focusing on almost the exact same segment for both images. And then it's going to start to see the difference between cat ears and dog ears. And then that difference allows the machine learning algorithm to do really well and distinguish between the two problems. That's it. I mean, that's literally the intuition of this. There's actually some really nice papers that I've seen where it's something that I've always wanted to do. I don't have code for that. I've never had a need for it, but it's something that it's always in the back of my mind. It's always been a project, I guess, I wanted to work on, which is doing exactly this thing here. So I build a neural network of however many layers, but then I just pick one layer, right? And I look at the image on that. So I've seen papers where they've done it. And what they do is they take the original image and then they just like highlight it somehow, put a little thing, you know, like a heat map or something to indicate. But it basically says, okay, this layer is looking at that, this layer is looking at this, and so on. But really, in a nutshell, that's the intuition of neural networks. Do you guys see that? So even before you start training your machine learning algorithm, you already define the architecture, right? So before you do anything, before you have even your data, you can go into TensorFlow and you know what your inputs are going to be. And you can just say, this is my network. So this is the outputs. This is the inputs. And I've got 3 hidden layers of, you know, let's say you already know that the inputs go to 784. And then you have, however, 100 here and 50 here and 30 here and so on. You see that? Yeah, go ahead. Yeah, that's a very good question. For the output is defined by the number of classes. Pretty easy. For the input is defined by the feature. So for instance, Iris had 4. MNIST is usually for images. The MNIST data set, which I think we've used in this course, was 28 by 28. We can take a two-dimensional array, if you remember from your data structures class, and make it into a one-dimensional array. So that's just 28 by 28, so that's 784. So you will see this number a lot in any machine learning course, and that's just because they all use MNIST. So just become familiar with it. So the input vector, this is the image. The 28 by 28, you just make it into a one-dimensional vector, right? You easily, with a for loop, can do that. To answer your question, though, now I said all of this because it's important to know where you're starting, right? You need to know the size of the input layer. The basic recommendation is to do the following. So just remember this. A funnel shape is basically the recommendation. You see, you know what I mean by that? That you should reduce the size of it. So if the input is 784 and the output, let's say, is 10 classes, every layer should be smaller. The reason for that is do more with less. Or another, like if I give you guys 4 months, not 4 months, 4 weeks to do a homework assignment, are you going to start right now? Probably not, right? You're going to wait, you're going to procrastinate for 3 weeks, and then on the last week, you're going to work on it, right? So you wasted 3 weeks. And that's kind of the same. So instead, give it just enough, right? So that the algorithm can learn from that. Sometimes you have to give it more. It's just it's required, but in essence, every hidden layer, this should go down. And also, this doesn't have to be 600 either. You can make a jump really quickly to like what I would do is probably go like at most 200, but I may as well might actually jump to 100. And so then this would make sense to be 100, and this would make sense to be 50. There is no equation, no magic. It's almost an art, and you have to do this experimentally. This is where transfer learning comes in, which is what I was talking about before, where how do you know which one's the best? Well, what usually happens for specific problems is you have competitions, you have different teams, let's say 20 teams come in, each one has their own architecture, however how many layers they had in depth, and then however many neurons they had, and then you find the one that was best and you kind of go with that. And then that's why transfer learning is great, because then you only use that model. You don't have to like take a year to figure out something that has already been figured out. Got it? Any other questions? No? All right, so that's the general idea. And this is where Marvin Minsky had said, if you remember, the evil villain in our story, right? that's not going to cut it. But as you said, right, everyone just jumped on this and they didn't quite see the second paragraph he wrote, where or his team wrote, where he said, well, if you add a second one, it'll work. But they're just like, no, he said it won't work. Right? And we're too tired to read the second paragraph. So anyway, so that's the idea. And hopefully this makes sense, because that's really all I can tell you about deep learning as far as intuition. And then after that, it's really just the little details of it. And although in this course, because this is foundations, we are actually coding from scratch, you will see at the end when we cover TensorFlow that you don't actually have to cover everything, right? A lot of it is abstracted for you. Remember, there's some calculus going on in the background as well, which is called the gradients, calculating the gradients, but we will see that as we progress, right? As we start getting into linear regression and logistic regression, I will kind of point those things out. We don't do any of that calculus, for instance. That actually is the main thing that things like TensorFlow and PyTorch do for you, the calculus. Now, one last observation I want to make before I continue. We had talked about how many weights we would need, right? So for this model, think about it. It is 1, 2, 3, 4, 5 times 5 plus 5 times 4 plus 4 times 4 plus 4 times 3 plus 3 times 2. And this is by no means big. This is tiny, okay? So yeah, think about, you have to literally learn all of these weights and the biases, which I've actually just, taken out, but it's just an equation that has this additional component. And that component is also random. So you just have to find out what it is. But just think about the weights. Now this is this is tiny. This is like insignificant. There's real models nowadays will have, the input will be something like this, 1 to 40 tokens, right? But this is 1 to 128 a representation. So it's basically like vectors of this, right? Vectors of 128, but you have 40. So it's almost like an image that is 40 by 128. You see that? But this, if you then do, you need to vectorize it. So now this is 40 times 128, right? Every single one of these things is a neuron. And it's every single one of them needs to be connected to the neurons in the next layer and the next layer and the next layer. I mean, we're talking about millions of parameters. So in Keras, actually, I think we will do this when we run Keras. We will print out literally how many parameters have to be calculated. This could not be done before without GPUs. Make sense? All right. And that's why, and so that takes us in conclusion, weights are extremely important. They are literally, look, I'm going to put this next to the word weights. I'm going to put this. Hey guys. That's how important they are. We're almost getting to a point where people will bring you bags of money just for these weights. Okay? And that's that whole idea of transfer learning. Okay? All right. So there's a website called Hugging Face. I don't know if you guys have heard of Hugging Face for machine learning. I always forget the name. And this is basically a community of machine learning models, just of something called transformers. Each one of these, notice Helsinki NLP, each one of these is a model that they've trained on some data, and it's got the weights. And then if you have a specific problem related to Japanese characters, right? I don't know, something, right? And you have a specific problem related to that, you get that model, you get their weights, and then now you can use their model as a pre-trained model to solve your own problem. Got it? And this is, there's thousands, I'm pretty sure, of models here. You guys can do, let's say you did a semester project, you finished, you load it up here. And then you make it available. Okay? And it's all about, all of these pretty much are the same neural network, a transformer with specific, but the weights are the thing of value here. Okay? All right. So I think that's a good segue actually then to get back into the code. So we're going to say then, if you remember, we were at fit and predict. What do we want from fit? What do we do with fit? We take the X-train data, right? We take the X-train data, and we take, what else do we need to train a model besides X-train? What else do we need when we train a model? X-train and what else? You've already used this. So what is it? Huh? Y-train, yeah. Very good. We need a Y-train. And what is this model going to give us when we train it? We have a model that's trained, but in particular, the weights and the bias. And so once we have these weights and biases, if you think about it, then we go into our predict model. And our predict model will do what? We'll take the X test data, right? Remember that? Takes the X test data. But the architecture should be the same in both. But what do we need to be able to use this predict model? The weights and the bias that we just learned in the fit process. Exactly. Very good. That's it. You see that? That's how it works. So this encapsulates really neural networks, in essence, how they work. You have architecture, which anyone can do, but getting those weights and biases that actually, and good ones. I can give you random ones right now, right? But getting good ones that actually work and obtain the good results are really where it's at, where you need all the computing power, where you need all the algorithms, and more, and very importantly, you guys are not Google. So you don't have 2.5 terabytes of a common crawl, as they call it, which is basically just, you know, they have crawlers and they crawl text of whatever and of the source that they want. So maybe they want just news articles, right? So Google can get all the news articles they want by doing a common crawl of news articles, or they want just you know, tweets. So Google could do that, right? Although tweets might be governed by some law of Twitter, but they can do other things, blog posts in Japanese, or 100 languages. What if you want a common crawl of just regular text? That's why it's called common crawl of text, but from 100 languages, so that you can train a model that understands different languages, right? You guys see that? That data is extremely important, in, you know, Facebook, Google will have it, OpenAI, but not necessarily everyone. So I'm working on a project right now, for instance, where the person I'm collaborating with is interested in like botany, right? It's an area of biology, right? And they're studying, I think, fungi. And so they, what do they do if they want to study fungi? They go to Wikipedia and just, you have a list of all the words related to fungi, right? The species and everything, and grab everything in Wikipedia that has every article that has that word in it. You guys see that? That's a common crawl of fungi, right? How big is that going to be? Could be a couple of gigs. That seems impressive. But in today, that's not very impressive, right? So what should you do? You want the weights and biases of a common crawl of all English language, for instance. You see that? So somebody that did not just Wikipedia, but did the internet, and so you do that, get a couple of terabytes of that, train a model. That model speaks English very well, understands grammar really well. Get the weights and biases of your model, predict, and now what you will do is your model will have an additional component called fine tuning. You see that? And what you do with fine tuning is, well, we're not going to use this one, but with fine tuning, what you're going to use is you take your own, you take the original weights and biases, right? The original weights and biases, plus you're going to train now just on a little bit more. You see that? So the way to visualize that one probably is like this. And don't worry about the perceptron, so we'll get that code done in a sec. But going back to the idea of a neural net, right? So you're going to give it some inputs. Everything in green is going to be all the weights from the pre-trained model. Do you guys see that? That's the pre-trained model. But now you're going to add new layers here, because you have a different output. You want to, let's say, just to keep it simple, you know, fungi, not fungi, whatever, right? So you're creating a new problem. You're going to add a couple of layers in here that were not there before. But you're going to use the original architecture from the pre-trained model. So all these weights in green, you know, all these weights, right, in green, what do you do with them? Usually I've said whenever we train, right? So we're going to train again. fine tuning is still training. That means I'm still going to give it new inputs, probably text about fungi, and new classes. Is it fungi, not fungi, right? I'm going to do that. So I'm still going to start at the input, go through the entire network until the end, right? You see that? I'm still going to do that. But I added a couple of layers here at the end, which are new, which tie to this problem. I still need, and the last thing I need to do is I just need to do a little trick. There's a way in the program to say all the green weights should not be modified anymore, right? So we're going to make these static. So all these weights now stay there, because if you remember the intuition, remember points, little lines, little curves, little triangles, ears, etc. You still want that, right? If you were trying to detect maybe, let's say just change it from fungus to non-fungus and change it to the image example. Let's say you pre-train on dogs and cats, but now you want to detect rabbits. You see that? So you could still use everything that you learn about dogs and cats, at least focusing on the ears, right? You know how to find the ears, but now obviously the ears of a rabbit look like that, right? So it's going to be a little bit different. And so when you're training, even though you're still giving the model inputs and it's still producing outputs and it's still going through the entire network, these weights, when you do feed forward, when you do the back propagation phase, you no longer update these weights. They stay static, and the only ones that get updated are the ones in these new layers, because these have to be learned because you haven't learned it. And that's called fine tuning. Make sense? That's it. So these are the basic philosophies that you have in this idea of deep learning. So let's go back now to, let's go back here. So that's why, we do the fit, and then we've got the weights and the biases, but we're not doing any fine tuning. So I'm going to take that out, but you can imagine how, we would have to adapt for that. So now we've got the weights and the biases, and then the predict function, which will take the X test data. It needs to use the weights and biases that we learned, and now it needs to predict Y pred, right? Which is going to be the predicted values, if you remember. Got it? All right, and then obviously we need to define those. And then once we have the predicted values, what we want to do is we want to compare. So we have the predicted values, and now what we want to do is we want to compare. So you do compare Y pred, comma, compare Y pred to Y test, basically. Right, so you're going to compare those two. So we already have that function, actually, right? We have the accuracy function. We've used that before. So it's going to be accuracy. And this just takes Y test, comma, Y pred. Okay. And so once we have that, we can take a look at the results. We can also probably print out, because this is a matrix, right? We're giving it Y test as a whole. So we can print out just compare. So we can print out Y test, just like the first 20. And then also we're going to compare, or print out, I should say, Y pred. Okay, got it? So this is the basic idea here. All right. So now what remains is we still need to define these functions, right? We need to define basically fit and predict and accuracy. So let's go up here. So I'm going to define accuracy. And actually, let me rename this. Yes, let me just make sure I'm working. Yeah, all right. Okay. All right. So Perceptron 2022. All right. So we have our function define accuracy. You should be able to do this function by yourself already because it's the same one we've used in the past. So it's going to be y true and y pred. Y true and y pred. And here we just need to define something. So for now, I'm just going to say return accuracy. Okay. We also need to define fit. Define fit and predict. So fit returns the weights and the biases. Okay. But we still need to define that one. And we also need to define predict. And we may need a couple more just to finish up what we're doing. And predict will return the y pred. So the return the predicted value. So y. Okay, so this is the structure basically. Okay, so let's start with, I guess the fit is gonna be the one that takes the most work, obviously, because a lot needs to happen there in the training. So let's just go with predict first. So predict takes the X test data, comma, and it also takes the weights, and it also takes the bias, right? So it takes that information. So now in here, we need to do something. Basically, for the perceptron, the equation is very simple. We just use remember this equation? This is the equation that I've been talking about quite a bit. You should be familiar with this. It's the equation for a straight line. We have an input, we multiply it times a weight plus a bias, we get what we need. Why is that a neural network? Hopefully you've noticed that already, right? You know, we've done a lot of neural networks today. Let's keep a simple one. We have 1, 2, 3, right? And then we have 1. You see that? And then now I have connections. And I have W1, W2, W3, X1, X2, X3, Y. You see that? So Y, if we start with Y, what is Y equal to? Y should be X1 times W1 plus X2 times W2 plus X3 times W3. You see that? And that's it. So this model that we've been writing is that. You see that? Plus, remember, the bias. So every one of these outputs will have a plus B, and that's just a parameter that gets added into the calculation as well. So, but usually you'll see people just ignore it to keep it cleaner. And if you think about this equation, if you think about it in NumPy, we can perform this operation as what? As vector multiplications. Do you remember that? At the end of the day, we need to arrive at a number here, right? Y needs to be a number. So really, this can be x1, x2, x3 times W1, W2, W3 plus B. You guys see that? And so really, our original equation Y, W times X plus B now is just, we just use the vector formulation of it, which is going to be W vector times X vector plus B. And that's where NumPy shines. It allows us to do this very neatly so that we don't have to like write all of this out, because if we had 784 features from MNIST, we have a problem. Right? You're not going to want to do this 784 times. And then you might say, no, I'm going to solve it with a for loop. And then what did I say about for loops in machines? Too long. You do not want to do that. That's, it's not going to work. And that's why in the 80s and 90s, people weren't doing this. They weren't making all those connections as it's done now. All right, but with matrix multiplications, linear algebra, basically, you can do this efficiently. And in particular, the libraries that we've learned in the class, NumPy, and we'll look at TensorFlow later. Just be aware that engineering people, like if you know engineering people, they'll talk about MATLAB. And they do things in MATLAB. And MATLAB, why are you doing NumPy? You just use MATLAB. MATLAB is great. Don't get me wrong. It's very powerful too. It's a tool. It's just not the common tool in data science. So most data scientists will use Python. After that, they'll use R. And if they're talking about MATLAB, they're from the engineering. They're probably like mechanical engineers doing data science. I wouldn't be surprised. Still very powerful. It's just everyone comes from their own background, basically. All right, so that's so hopefully this made sense, right? So I jumped from this diagram format, right, to the equation, right? You guys see that? I've gone to the equation. Okay, and so I'm about to throw this at you in the code, right? This operation, okay? But I'm not gonna write it out. I'm not gonna even try to do the math of it in vector form in NumPy, although I could. It's always better to just use the built-in functions of the libraries, always. So whenever possible, use the libraries, because you always end up with little things like divisions by 0 and things like that. And the functions always handle that really well. Okay, so it's always better to use the built-in functions. But just be aware, I'm literally doing this. Okay, so I'm just going to switch over to the equivalent way, or the efficient way, I should say, of doing this in our code in Python here. So I'm going to do linear output, right? Linear output. And instead of doing the multiplication, I'm just going to invoke NumPy, NP, and I'm going to use NumPy's very efficient dot. This is called the dot product function that NumPy has built in. And it just allows you to do this without having to worry about things. So in fact, it is so efficient that we don't even have to do it on a vector basis, because let's say that I give you 50 samples or 120 samples, right? What's your intuition again? I'm going to grab each row in a for loop. Again, inefficient. So NumPy allows you to take the whole matrix and multiply it times the weights vector. Do you guys see that? And so instead of a for loop that would take, let's say, several minutes, you do it in one shot like this, takes seconds or fractions of a second. All right, so here I'm going to give it the whole X test, I think, because we did 20% split. So it's 20% out of 150, that's 30, right? So there's 30 samples in here. but it's going to do all of them at once. So X test. And then what do you multiply it times? The weights, right? So the weights vector. You see that? So we multiply it times the weights. And then what else do we have to add to it? The bias. That's it. You see how simple that was? Now remember, these values are going to be linear. So now we need to talk about the fact that we're trying to build a perceptron. We're trying to build a model that is not linear, but nonlinear. Okay, intuitively, again, I mentioned this on Tuesday, I remember. Intuitively, again, going back to the villain here, right? Marvin Minsky, who said, yeah, you think your model is so great and everything. Solve that, right? And you can't, right? So there's no straight line that will do that. But what we have here, what we have in our model here so far, what we have in our model here so far is that we can only create straight lines. Because what is this? This is the line equation, straight line equation, right? So it only handles straight lines. So we need something that allows us to actually make the transition to non-linear, all right? So that intuitively, we can approximate something like that. Now, this is just an example, obviously not for our own data. We're not creating this, but you know, maybe a better example of this would be like that, right? So yeah, something like that. So a straight line may not be perfect for this one. We have one there, but a curve, you know, might be a little bit better, right? So that's nonlinear. We're able to create a function that it's no longer a straight line. It is now not linear, right? So, you know, where we had x plus b, we run this through a function, and now the result is that this is going to be, let's say, x squared plus b, right? B squared maybe. And so now, well, x squared is a quadratic. It's no longer a straight line. Or we change this to be x3 exponential 3, and these are called polynomials, right? Or whatever. But we are at, I forget what the equation for a circle is. You guys probably remember it better than me. So you could convert it to that. Do you guys see that? The point being that we need to take a straight line that we had and make it into, yes, a curve. Very good. Okay. So how do we do that? We need to run it through a function. This is the nonlinearity function. It's a very important concept, right, to be aware of this. Just be aware that in deep learning, it has been established that probably the best one is something called ReLU. But we're not there yet. So we're not there yet, but just be aware that's kind of the one that is used. Remember, we're talking about the original perceptron from the 50s. So, you know, so we're going to use something else. All right. So that being established, we're going to go over here and we're going to take, that's why this output is called the linear output, because we still need to make it nonlinear. So that means that our y-pred is going to need an activation function. Okay, you guys see that? So this is the function I was talking about. Usually the term for it is activation. I think that actually comes from neuroscience, where they thought, do the neurons fire, they activate, something like that. I think that's where it comes from. Not sure really. And so what do we input in here? The linear function itself. So we input the linear function, we run it through the activation function. There you go. You have your nonlinearity. Okay, got it? Any questions? All right, so, and that should be it actually, but first I have a typo here, activation. Now, because I threw this in here, that means that I actually need that function as well. So I'm gonna go ahead and create, I'm gonna define activation function. So I'm gonna define this, and I need to come up with something here. So return, for now I'm going to return 0, but I need to return a value here. You guys see that?
When we plug in linear function into the activation.
Yes. Oh, right. Linear output, right? Is that what you mean? Yeah. Sorry, that was my mistake. It should be linear output. Good catch. Now, activation function, as I said, the idea of going from straight line to quadratics or polynomials, that's something that has evolved over time, right? And that's where we are today. In the 40s and 50s, when they created the perceptron, they didn't have, in particular, because they didn't have the computational power, right? They didn't have the ability to just create those things, do those things back then. So the activation function here has a much simpler role, okay? Has a much simpler role. Remember that when you basically this gives you a value, and then those values just get converted into other values, right? At the end of the day, the point of a function is to take any value, a real valued number, and convert it into another real valued number. The fact that it's nonlinear is that, like in a sine function, right? Classic example. You give the sine function a value, and then the outputs are always like this, but it doesn't give you this at once. It just gives you the little points, right, over time. So those, values get converted into values. Values get converted into values. So in our case, for the perceptron, it was actually very simple. All it does is the activation function in the perceptron just gets a value x, which you can think of x as any real valued number. X is, basically minus infinity to plus infinity. Do you see that? Any real valued number. And so really what they did with the perceptron is they just said, well, we're not even going to get very complex with mapping it to nonlinearities because, by the way, it's 1940s and we don't really know that very clearly yet. So instead, we're just going to say if the value is greater than 0, is this class? Or sorry, if the value is, less than 0, is this class. If it's greater than, so if it's positive, it's one class. If it's negative, it's another class. Do you guys see that? And we're going to teach our models that way. So our labels need to be in such a way, right? Where we say, so this is a binary classifier where you're just giving it pictures. Is it a cat or, or dog? Or is this a circle or not? That kind of thing. It was very simple, right? So actually to do that in numpy and other languages, we can just do np.where. And then we just have something very simple like saying, well, if x is greater than or equal to 0, because it could be 0, then the value is 1. Else the value is 0. That's it. Pretty simple, right? That's the activation function. It is, it does convert the data though into so it was any value from infinity to minus infinity, let's say, and now we've kind of made this function a step function, right? So, 0 or a 1, right? So basically, the function that we implemented kind of looks like this. take a look, the activation function that we have here, basically, this is 1. We said 0 or 1? Yeah. Zeros right there. So I'm going to use a different color. So really, that's the function that we implement. Do you guys see that? So this is the y and this is the x, right? So the x can be any value like that, right? From any direction. But if it's less than 0, it's this. And if it's greater than 0, it's that. So this is usually called a step function. And it's one of the activation functions that we're using. Other versions of this might be to use what is called a sigmoid, which is a little bit like that. It's a little bit more curvy. And that's better because it, here it's just like it's this or that. Here it's a little bit more like in between as well. You see that? Does this make sense? So I mentioned this because we're gonna come back to the sigmoid. And so I wanted you to be able to relate it back to this. Okay, yeah. They make a single line? What do you mean by that?
Remember how you said with the perceptron,
Mm-hmm.
you said you needed a curve? What if you just made the line wider? Would you do that scan more at once? Or is that not the point?
I think you're talking about something I said here. Okay. What? So you said this is a line, and if I understand you just make it longer? Wider. So you may, instead of a line like a rectangle? Well, let's just see what you mean. So this is a line. What you're suggesting is instead of a line, do something like this. For what purpose? Because the line really separates, right? So what are you trying to do with? You're trying to group them. So you want to just do that. All right, but that's like clustering. That's a different thing. The straight line, your straight line idea actually has some merit in the sense that, in the sense of this. So if I just draw this straight line, that works. If I draw this one, it works, right? In theory. But if you want to be perfect, if you drew this one, that would be the best one. So the rectangle idea would be, well, if you maintain a margin, right, that's like that, then this assures that you will get this one because it's not this line that things have to be on either side. It's these lines, these boundaries. So this certainly would give you a better line, a better fit, if you will. So I can see how that could be the rectangle idea you have, because this is technically a rectangle in the sense that you have the samples. If a sample is here, that's an error. But if it's here, it's okay. You see, so these are constrained boundaries, I think it's called. Support vector machines uses this. And before neural nets, this was actually 10 years ago, this was actually the way to go. Yeah. But non-linearities, but actually I should stress, this is still a straight line. So it's still solving things through linear functions. Neural nets curves or create curves, don't need curves. They're universal function approximators, which means they can approximate any function. And experimentally, well, they beat this one. So I can't really tell. I mean, it's like they won. So there's that. So it's a good question, I think. Yeah. So anyway, so we were in the code. So let's go to, oh, so we did the activation function. So that one's ready, right? That's ready to go. The predict, I think, is almost ready to go. And then let's just do the accuracy, which you guys should already know how to do. And then we'll stop there. And then we'll finish up the more complicated function, which is the fit function on Monday. All right, so that way, because that one will take a little bit work, but we've laid the foundation. We'll just use this code. You can also already look ahead if you want to look at the GitHub itself. So let's do accuracy here, which would be accuracy equals numpy.sum. And then you're going to look at, just like we did before, the values of y true, compare them to the values of y pred. This will return a whole bunch of ones and zeros. So ones when they're similar, zeros when they're not. And then you can just sum that and then divide that by the length of y. All right, and that should give you your accuracy. So I think, yeah, this is a good stopping point. We've defined the activation function. That's actually a big accomplishment. We've defined the predict function. We've defined the accuracy function. And all that we have left is the predict a fit function, which will be, a lot more of the code on Monday. And then after that, we will also continue with, once we finish the perceptron, we're going to go gradually to the next step after the perceptron, which is actually linear regression. Linear regression is something that when you took your statistics course, you should have already learned a little bit about it. So that's good because it'll give you some foundation on it. So if you want to refresh your memory by looking at some of those notes, that'd be a good idea. But it's not common. And I'll start. I'll give you the basics. All right, so I'm going to save this file. And then I'm going to stop the recording. And then if you guys have any questions,